Okay, so we're going to have a look at how to calculate the area of a triangle given the polar coordinates of its vertices. So we'll start off with this scenario where the origin is contained within our triangle. There's a nice little trick we can use here, which involves splitting up our triangle into three smaller triangles. And this turns out to be really useful here because there's some information about these smaller triangles which is much more readily available than information about our overall bigger triangle. So we focus in on this triangle in the top right. What information do we have about this triangle? Well, we know from the coordinates of these 2 points that the distance from the origin to this point at the top is r2, so this side length here is r2, and the distance from the origin to here is r1, so this side length is r1. We can also work out this angle, I'll just call this alpha for now. We can work out this angle using the values of θ2 and θ1. So then we can just use our formula for the area of a triangle, a half times r1 times r2 times sine alpha. And this gives us the area of one of our smaller triangles. So unfortunately, it's not quite as simple as just saying that alpha is θ2 minus θ1. I'm not going to go into all the details of this, but basically if you calculate θ2 minus θ1, you could get this equal to alpha, which is great, or depending on how these are oriented, you could also get the negative of the angle that you really want, so minus alpha. So when we do sine of minus alpha, this isn't any good, sadly. And another problem we can get when we calculate θ2 minus θ1 is we could actually end up with the reflex angle on the outside of our triangle, which is not what we want. So you could get 360 degrees minus alpha or 2 pi radians minus alpha. And the final problem you could get as well is the negative of the reflex angle, so minus 2 pi minus alpha could be your value when you calculate θ2 minus θ1. So we won't go into all the details of how this works, but basically if we draw a sketch of the sine graph, let's imagine that your point alpha is over here, then let's have a look at some of our different values. 2 pi minus alpha is over here, but you can convince yourself using symmetry of the sine graph that sine of 2 pi minus alpha, we just need to take the absolute value of this. And we can do the similar sort of trick for sine of minus alpha. So all we need to do in the end here is sine θ2 minus θ1, just take the absolute value of this, and this will be equal to sine of alpha, which is what we want. And when we have the negative 2 pi minus alpha, we don't even need to do anything here. This turns out to be the correct positive value, but taking the absolute value of this doesn't cause us any problems. Okay, so what can we conclude then? Well, we can conclude the area of this small triangle here, and the total area then is the sum of these three small triangles. So we've got half r1, r2, then the absolute value of sine θ2 minus θ1 for the area of our first triangle. Then we just need to add in the remaining two triangles' areas using the same sort of argument as before. And we get a nice expression for the area of our triangle, at least in this scenario where the origin is contained within our triangle. So now if the origin isn't contained within our triangle, there are actually two subtly different cases we have to consider. So we'll start off with the first one, then we'll have a look at why these two cases are different. So we're using the exact same trick as before for our first case. We can split all of this up into lots of smaller triangles. You can see now we get a quadrilateral. So we can't just add up the area of the three smaller triangles, this is going to be too much. We're only interested in the area here of the triangle at the top. So how do we actually calculate this area? Well, what we could do is take the area of two of our smaller triangles, then we've got to take away this area of the triangle at the bottom. So just kind of informally, pictorially, how we would draw this is the area of these two triangles added together, then we've got to take away this small area at the bottom. Then symbolically, using our formulas, what does this look like? So if we've got r2 θ2, this is the one that's sandwiched in between r1 and θ1 and r3 θ3. We'll make this notion of being sandwiched in between them more rigorous later as well. But basically our area then is equal to a half r1, r2, absolute value of sine θ2 minus θ1, plus a half r2, r3, absolute value of sine θ3 minus θ2. Then we've got to take away a half r1, r3, absolute value of sine θ3 minus θ1. So this gives us the area in this configuration. But then if we have a look at the next configuration, so here our r2 θ2 is kind of on the other side of this line, so it's closer to the origin than in this scenario. Pictorially, what we need to do now is we'll actually need to do 2 subtractions rather than the 1 to get the desired area. So we're only interested in this area here. So what we can do is we can find the area of the total overall triangle here. Then we need to take away one of the small triangle's areas, and we also need to take away the area of this small triangle here. So this tells us then that the area of our triangle we're interested in, the one shaded in red there, this is going to be a half r1, r3 absolute value of sine theta 3 minus theta 1. Then we've got to do 2 subtractions. We take away a half r1, r2 absolute value of sine theta 2 minus theta 1. And we've also got to take away a half r2, r3 absolute value of sine theta 3 minus theta 2. And then if you compare these two area formulas, you can actually see that one is the negative of the other. So we can combine these two cases into one just by taking the absolute value of everything here, because the area is always going to be positive. So now we've got a formula which works in both cases, but at the moment our approach relies on having to do a drawing each time to check if the origin is contained within our triangle or not. And there's also in the second case this business of choosing the point with coordinates r2, theta 2, so that this is sandwiched between our other 2 points. So we start labelling them now. We're basically saying that we need the point P2 to lie in between P1 and P3. So we need a way of making all of this a bit more rigorous before we're finished. So the first thing we need is a nice way of describing the non-reflex angle formed between a point, the origin, and another point. And basically to get this, we can look at the difference between our angles from our coordinates. We take the absolute value of this, but then also the minimum of this and 2 pi minus this angle. And you can verify for yourself if you like, this is going to guarantee that you get the non-reflex angle version by taking the minimum of these two. Okay, so now we can use this to distinguish between case 1 and case 2. So let's have a look at what happens in case 1 with our non-reflex angles. Well, because the origin is contained within our triangle, what happens when we sum all of these angles? They just sum to 2 pi, or 360 degrees. And it turns out that when the sum is 2 pi, this tells us that we're in case 1. And if we compare this with the second case, where the origin isn't contained within our triangle, let's have a look at what happens with the sum of our non-reflex angles here. So we have this angle plus this angle here. You can see these are relatively small. Then we also add in this bigger angle, but the sum here of these 3 angles is not going to be 2 pi. The sum is actually going to be less than 2 pi in this case. So do spend a bit of time trying to convince yourself of this, if you like. But basically this tells us that we're in case 2, where the origin isn't contained within our triangle. Okay, so now how do we choose, let's imagine we're in case 2, how do we choose our point P2 so that it's sandwiched in between P1 and P3? Well, this is actually relatively easy now that we've got this framework for describing these angles. We basically just need our points P1 and P3 chosen so that we've got the biggest angle between P1 and P3. So if we just calculate all of the different angles between our points and the origin, we just need to choose these so that the angle P1 to the origin to P3, this has to be bigger than the angles involving P2. Okay, so let's just quickly summarise what we've got then. So imagine we're given the coordinates of some points which form a triangle using polar coordinates. The first thing we do is we calculate all of these non-reflex angles, then we add them up. If the sum is 2 pi or 360 degrees, we can use our first formula to find the area of our triangle. In the second case, if the sum is less than 2 pi, then we might need to potentially relabel them so that P1 and P3 make the biggest angle, and then we use our second formula for the area of the triangle. And if this seems like it's all too much effort, you could always convert to Cartesian coordinates and take it from there.